So hi everyone. Last time we discussed the Wiener process. So let me just review the Wiener process in just a second and then describe the evolution equations that we anticipate under sort of noise added to our Newton's equations. So very briefly, we had said that sort of the intuitive definition of our Wiener process was that the integral from some t double prime to some from some t prime to some t double prime of the Wiener process itself is sampled or is drawn from a normal distribution with zero mean and a variance or standard deviation of 1. So let's go ahead and, given this definition of the Wiener process, write down what our evolution equations are. So we had a q t double prime equals q of t prime. I'm just writing down what we had before. Now we don't expect many changes here. So p of t prime plus, in our position, we have the integral 1 over m t double prime, t prime to t double prime, d tau. I'm just looking at my notes here to make sure I don't get my primes screwed up. D tau prime, f of tau prime. In general, this is going to be a q of tau prime if it's a position-dependent force. And then plus c dw of tau prime. That's for the position. So remember, the only difference now is that instead of having just a plain force, we have force plus this noise. And then we have a p of t double prime equals p of t prime, integral from t prime to t double prime of t tau, f of tau, q of tau, and then plus, the noise portion. This is the only difference now, from some t prime to some t double prime of some dw t. And now we ask ourselves the question, under the same approximations that we made last time, what changes? Well, the first thing that changes is that we recognize immediately that this term, irrespective of whether I have noise or not, has a delta t squared term because of these two integrals here. So sometimes, people will say it's order delta t squared. So we've already chosen to eliminate those terms and not keep track of them, assuming that our delta t is sufficiently small. We have ended up with kind of an interesting term here that we need to keep track of. And that's really the term that I will now write out a little bit more explicitly. So I'm going to rewrite this term using maybe the second, slightly less intuitive definition that we had of the Wiener process. So I'm going to go ahead and erase everything, but I'm going to focus on this term right here. So first things first, I have a q of t double prime is approximately equal to q t prime plus my time interval t double prime minus t prime divided by m multiplied by p of t prime. This is 2 primes, that's 1 prime. That's my delta t. Then I have my p of t double prime is approximately equal to my p of t prime plus my time interval. Now I remember here that I have an f of t prime q of t prime. And why is it f of t prime and not f of t double prime? Well, the fact that I can write again force and multiplied by the interval delta t suggests that the force was sort of independent of t. I could pull it out of the integral and then multiply the interval by the force. And then finally plus c square root, and this is the slight rewriting that I alluded to earlier, t double prime minus t prime z, where z is drawn from a normal distribution with mean 0 and variance 1. Now, what have I done, or how is this different? Earlier, remember, I had written this as the integral, if we recall, of dw. But my integral of dw is simply, the equivalent of the scale that I'm integrating over, sort of the standard deviation, multiplied by my normal random variable. So the larger the delta t, the larger the effect of the noise, because the more the noise spreads, and it spreads in proportion to the interval. And in this particular case, I have to include the standard deviation here, so it appears as the square root of the time interval. If I were to write these equations in discrete time, basically exactly the same equations, I would write them out as qn plus 1 equals qn plus tn plus 1 minus tn pn over m. This is exactly identical to what I had last time. But now I'm going to write pn plus 1 equals pn plus tn plus 1 minus tm times f of tn. Again, exactly the same as what I had last time. And in principle, again, if it depends on position, then I can put a qn here. Plus c, and then square root tn plus 1 minus tn xi of n, where xi of n is drawn from a normal distribution, mean 0, variance 1. So my position is, my future position is equal to my current position plus, delta t times p of n, within, again, this order delta t approximation. And my momentum is evolved according to both a deterministic component and a random component. So now the idea here is that I have a force, and as I've mentioned earlier, I have kind of little random kicks. Kicks can be left or right, because it's a normal distribution, so it's going to have both a positive and a negative tail, sort of inducing some uncertainty in the evolution of ultimately my positions, which may be what I care about. So if I were to keep track of my state, my qn, pn, and I go somewhere else, and I'm going to have some qn plus 1, pn plus 1, but they won't be deterministic. They're going to be sort of spread over some region. And so I'd like to be able to learn sort of what is my probability density, right, in going from some qn pn to some qn plus 1 pn plus 1. What is that probability density? Well, it's not going to be a delta function because now you're distributed over some region. In fact, because my noise is Gaussian, and sort of because the properties of the Wiener process, it's going to be a normal distribution centered at the value that you would expect had you had no noise, but now the variance will be dictated by the variance of that noise. And the variance of that noise, or I should say the standard deviation, we know is c, square root, sort of that time interval. So now we're going to go ahead and write down what the transition probability density is. And briefly speaking, my position at some future time, conditioned on my current position and my current momentum, still going to be a delta function because the expression for the position itself does not have the noise in it. So there's a qn plus tn plus 1 minus tn, and then pn over m. But remember now that pn itself is going to be random. So pn plus 1 conditioned on qn and pn is going to be drawn from a normal distribution with some mean pn plus tn plus 1 minus tn times f of tn, again qn. That's the mean. And then comma, and then we have the variance. And the variance is going to be c squared tn plus 1 minus tn close brackets. That's the variance. So now if I were to write out the full sort of transition probability, so the transition density, or transition probability density if I want, from Qn and Pn to Qn plus 1, Pn plus 1, that's going to be proportional to, well, the product of a delta function, again for positions, multiplied by the normal. Last time we had seen that momentum was also a delta function. In this case, momentum will not be a delta function. So the momentum will be normal and the position itself will be propagated given, or the momentum will be normally distributed and the position will be delta function distributed based on where I was last. So this is kind of an example of something a little bit less trivial. And this notion of sort of white noise, we will be seeing it very often as it pertains to sort of modeling dynamical systems. There's one little note that I would like to make before turning to sort of Brownian motion and diffusion to end this section. And that little note is just sort of talking about modeling under increments as opposed to absolute positions or momentum changes, for example. We notice here that all of our probability densities were expressed in terms of, where I start from and where I go. And, same is true for momentum, where I start from and where I go. But in principle, we could be talking about sort of what is the change in position and what is the change in momentum as opposed to sort of absolute positions. So maybe we can entitle this section Modeling under increments. So assuming that you have some kind of change. In this particular case, we'll say, for example, that my state at Rn plus 1 is my old state plus an increment, which we'll write as follows. And then I will say that my initial condition is drawn from some R1, and then my increment given, my increment given my previous position, is drawn from some distribution, which I'm going to call Gn Rn. And this is sort of a transition probability density for the increment, right? It may be more convenient to write these down for increments. I just need to be a little bit careful that the coinciding, this is the transition probability distribution, not density, for the increment. I just have to make sure that the coinciding probability density, so that G of n of delta Rn conditioned on Rn is normalized over all possible increments, right? So this would be the coinciding probability density. And that's normalized, like I said, over all increments. So in principle, we can go ahead and rewrite the equations that we had earlier for position and momentum using increments instead. It's not the most sort of insightful exercise, because in some sense it's a little bit trivial. Whenever we see some positions, a couple of extra deltas will appear in our expressions. But if we want, we can go ahead and do it. So just very briefly, now the change in position is equal to Tn plus 1 minus Tn multiplied by Pn over m. And then my delta Pn, my increment in momentum, is going to be equal to my Tn plus 1 multiplied by f of Tn Qn plus c, and then, I have a Tn plus 1 minus Tn in absolute value, square root times c of n. And again, the understanding is that c of n is drawn from a normal with mean of 0 and variance 1. So then I can write out, using these expressions, what my sort of probability density, transition probability density is for my increments given q prime and p prime, my initial conditions. And if I were to write that explicitly, I'd have a delta function, and I may run out of space, but let's see. Tn plus 1 minus Tn times p prime of m. Now I have to put the argument explicit, so it's going to be delta q, right? Because delta q is centered around this value at this point, and in fact with no noise, multiplied by the normal, and this will be for the momentum. So now the increment is delta p, that's my random variable, and then there's a mean and there's a variance. Let's go ahead and write out the mean in slightly smaller font. Tn plus 1 minus Tn multiplied by the force at Tn, and again I could put in Qn here if I wanted to, and that's the mean. And the variance itself actually doesn't change, so c squared Tn plus 1 minus Tn close bracket and close this bracket here. So there you go. That's the transition probability density in case that you have noise. In other words, your Newtonian dynamics are being modified. Your Newtonian dynamics are being modified by noise. So, like I said, this is in particular, the first two lines are a model drawn from classical mechanics. This is to this here is to introduce sort of noise. But there's different models. We don't necessarily just have to limit ourselves to classical mechanical examples. So, as another example, I'd like to discuss sort of Brownian motion. In discrete time. And what Brownian motion is sort of the random motion of a particle. And by random, we mean something particular in this case, which I'm going to spell out. Brownian originally comes from a person, Brown, and one of the first sort of demonstrations of Brownian motion, or something that seemed to satisfy the conditions, was sort of a pollen grain kind of jittering in fluid solution at some temperature. So let's go ahead and write down explicitly what we mean by a model for Brownian motion. What we're saying is that the position, and we're going to make explicit now the fact that we're looking at Brownian motion in 3 dimensions. So the position in x at the next time point, given where you started from, is drawn from a normal distribution. That normal distribution is going to be centered around where you started from, right? So you don't just jump anywhere. And according to this model, the variance can be written as Tn plus 1 minus Tn close bracket. D is sometimes called a diffusion coefficient. And if you notice, kind of the diffusion coefficient is related to the previous example we had, sort of related to the strength of the noise. So the more the noise, the more the spread in your momentum from the previous example. Similarly here, the larger the diffusion equation, the more your next position is sort of randomly distributed given where you started from. Now, if your diffusion coefficient is extremely small, then you're kind of sticking to sort of your neighborhood. Now, we said this is 3 dimensions, so we might as well throw in a yn plus 1 given yn, and a zn plus 1 given zn. And those are also drawn from normals, and they're going to be independent normals centered at the previous yn, previous zn, with exactly the same standard deviation. So in some sense, the 3 positions don't know about each other. This is kind of an example, a very simple example of sort of isotropic and sort of independent, homogeneous diffusion. Homogeneous meaning that, your diffusion doesn't depend on where you are in space, so this is completely independent of space. It's independent because the different positions at some level don't know about each other. So if you're a particle and you're starting off here, depending on what your diffusion coefficient is, right, so let's kind of draw this in 3D. You'll have some component of motion in the x direction, some component of motion in the y direction, maybe some component of motion in the z direction. So, maybe you're going to move your next position somewhere here, and then maybe your next position will be here, and then your next position will be back there, and so forth. So this is kind of Brownian motion in discrete position. If I were to write out all 3 dimensions sort of as one big kind of vector, then maybe I could write something like this down, where I would say that the next position, given the current position, is drawn from a normal distribution. I'll put a 3 here to make it clear that this is a 3-dimensional Gaussian. It's going to be centered at the previous position, and the variance itself, now you're going to have a covariance because it's a 3-dimensional Gaussian, so Tn plus 1 minus Tn multiplied by I. I here is the 3 by 3 identity matrix. Sometimes people write it out as I sub 3 by 3. Either way, if I were to write out what this covariance matrix looks like, it's 0, 0, 0, let's see, sorry, 3 by 3, yeah, so 2d delta t, 2d delta t, 2d delta t, and then 3 more zeros here. That's kind of what the covariance of this 3 by 3, the covariance of my 3-dimensional Gaussian looks like. And the mean is going to be a vector or an array with sort of 3 entries. Good. That's when I have absolute positions. What if I have increments? Okay, well, you might not be so surprised that I'm going to rewrite it as delta Rn, not conditioned on anything, is drawn from a normal distribution that's now centered at 0 because I'm only looking at changes from my previous position. However, with the same variance that I had before, Tn plus 1 minus Tn multiplied by the identity matrix. If I'm using increments in order to reconstruct a trajectory of a Brownian particle, I need to be a little bit careful because, the trajectory of the Brownian particle is not this increment and then that increment and then that increment, right? I have to start off from my position now, and then I have to add an increment, and then based on now where I am, I add my new increment and so forth. So this is how I would sort of write code in order to generate sort of a Brownian trajectory. So let's actually sketch that for a second, and I think this is in the textbook called Algorithm 2.2, which is the sampling of Brownian motion. So the idea is that you are given, some are not, some initial position, you are given some times at which you want to sort of evaluate your positions, and you're given a diffusion coefficient d. So then what you're going to do is you're going to draw a Gaussian random variable with some normal, maybe a 3-dimensional, so you can do all 3 dimensions at once. And then you're going to set Rn plus 1 equals Rn to 2d, and let's make these all vectors. And in fact, this would also be a vector because you're drawing 3 Gaussian random variables. So your next position, given your current position, plus 2d Tn plus 1 minus Tn square root multiplied by that vector. And then if you want, you iterate. Now, of course, you can do something a little bit more efficient. Maybe you can generate an array of 3 dimensionals so you don't have to iterate immediately and then plug that array in here and then sort of generate all of your positions immediately. But that's kind of another approach. The final dynamical paradigm. So let's just back up. We've just now completed sort of continuous space, discrete time. And we've discussed 2 models, the sort of Newton's equations, and we've also discussed kind of this Brownian motion example. For what it's worth, actually, the Newton's equations and the Brownian motion example are related. It's in the case where you ignore inertia. Now, it goes a little bit deeper into the physics. If you're so inclined, you can take a look at the advanced sections, which I think are preceding or sort of in the neighborhood of this discussion here. But either way, sort of these two paradigms, looking at Newton's equations and looking at sort of Brownian motion, are two examples of continuous space, discrete time. The last paradigm that I don't want to spend too much time on is a final paradigm, and that's continuous space, continuous time. I will only mention it, but I won't write much about it. Most of it is labeled advanced in the second chapter. And there's a reason for that. It isn't used very often, and in fact, it sometimes relies on equations that are very difficult to deal with. It also doesn't always naturally sort of align to sort of the experimental paradigm of thinking of things as evolving or being sampled in discrete time. So the idea is that it's left as sort of more advanced reading in case you want to read it, but is otherwise not quite used as often in modeling. So that sort of summarizes chapter 2. And I believe what we move next to is sort of likelihoods. And if I can just say a word about it, we've now completed sort of in chapter 1 ways by which to write down probabilities, ways by which to manipulate probabilities and turn them into, well, turn joint probabilities into conditionals or marginals. We've alluded to the notion of a likelihood. And finally, by the time we got to chapter 2, we sort of discussed common probability distributions we deal with when we work with dynamical problems. Now that we have sort of this baggage, the language of probabilities and the language of dynamical models, we're sort of ready to formulate likelihoods. So what I'd like to turn to next in chapter 3 is the concept of likelihoods. Thanks.